So in this video, I want to show how I make the orbit cards for this Tao Analysis book, um, and sort of talk about some of the difficulties that I run into. Um, so you can see I'm done with section 5.1, and I was starting to do 5.2 and 5.3, and it's been a while, so I need to sort of find my place and then start thinking about what cards I want to make. So here we go. Okay, yeah, so 5.2 was a pretty short section, and like mathematically the only thing that's really necessary is this definition of equivalent sequences. So there's really not a lot of content here, and um, let's see what I did. Okay. Yeah, so let's see. Yeah, I have the definition, and I'm a little unsure if this is like too long because um, as you can see, it's three nested quantifiers, uh, which is kind of tricky to do in your head if you're still learning this stuff. Um, and then there's this motivation one, which I think is fine. Um, yeah, then there's always uh, these examples that I could add. Like, yeah, I guess I could add this. Then I also want to add another sequence or like two sequences that are not equivalent, um, but that someone might think are equivalent. So let's start by copying this, and I'll copy that. Okay. So how about something like are the two sequences yes, and then um, what is a good sequence? Actually, I have another positive one that I want to use. So it's gonna be 1, 1/2, 1/3, 1/4, 1/5, dot dot dot, and then this one is gonna be cut in half each time. So 1/8, 1/16, dot dot dot. And of course, both of these go to 0, so they're equivalent. Now I really need a no answer. And the reason I'm doing this is because I don't want the person answering to kind of pattern match, like whenever they're asked, are these sequences equivalent? Like right now we have 2 yes answers. So they might start to like pattern match and say, oh yeah, whenever I'm asked, are the 2 sequences equivalent, I just say yes. And like that's not good because then you're not even thinking about the 2 sequences involved. Let's see, what's a good example? I might do the reciprocal version of this. Then let's just make sure that this definition works. Yeah, so the gaps are growing each time. So even though they're both going to infinity, they're not considered equivalent. I might add that as an explanation. Even though are blowing up. It's not shrinking over time. So okay. Yeah, I might want another decimal one, kind of like to visually camouflage against the first one. So let's see. Yeah, I might just add like uh maybe this one's going to 1. Or like that one's going to 1, this one's going to 0. So like 0 0.1, 0 0.01, 0 0.001. And I actually like this example because like if you look at the terms together, their sum is always 1, which is kind of like, it looks like a pattern, even though it's not like the pattern we want. So there we go. And I can add Yeah, I guess I don't really want to say like converging. Uh, I'll say like um, shit, no, I got that wrong. It's there we go. Okay. Um, um, 2, 1. Okay. Okay, I think, let's see. So we have some examples. We have the definition. So this one, it's another definition that's like, yeah, not used anywhere else. So the way I'm probably going to deal with these is um, I'll make a separate page for readers who want the like Tao-y definitions, and then the rest of the people can just use this section 5.2 page with all the standard cards, um, so that like um, it's more compatible with the rest of the like textbooks and so on that they might use in the future. Um, okay. Yeah, and then this kind of proof is um, not that good for these small cards. That like you want to be able to answer these in a few seconds each. Um, and I think this kind of proof is better reinforced by the exercises, um, and also what I call proof cards. But yeah, I don't want to do that with these orbit cards. So um, I think that's like it. Um, Looking at the exercises now. Um, hmm. They're like kind of interesting facts. Um, I'm wondering if I should add like yes, no questions, and like make some of them yeses and some of them no's. Um, but I don't know if that's like actually good practice here. Um, or like uh, if just solving the exercises would be enough. Yeah, so I think I'm gonna just like uh, see, I'm gonna test out these cards. Uh, okay, so um, yeah, I think there's like 1, 2, 6 cards. Okay, then I come here, change that to that. Okay, 6 prompts. So it looks like we have a new version here. Okay, definition of two sequences being equivalent. Um, for every epsilon, there's some n such that there's some big N such that for all little n greater than or equal to big N, the distance between a little n and b little n is less than or equal to epsilon. See, that's a mouthful. And it would be fine if I was writing it down. And for my own cards, I do often have a piece of paper and pencil and like write stuff down. But then here we're like trying to bring spaced repetition to the masses, kind of. So we want to make it as easy as possible. And I'm still not sure how best to do uh, these kinds of definitions because they are important to know and like you really do want to be able to rattle them off. Um, yeah. I might just leave them in for now and then see if someone complains. Uh, yeah. Okay. What is the motivation for defining equivalent sequences? Um, yeah, it's something like when we're constructing the real numbers, we want to say when two numbers are equal without like having already constructed the real numbers. Um, yeah, okay. Oh, I do like how they line up. Um, so this one's a yes, and this one is also a yes. This is a no. Oh, the gaps are so they are not considered equivalent. Okay. No. Okay. Oh, then I can get rid of this debug uh, and also update the index. So this is 5.2. Okay, it's here. Okay, what's going on here? 5.2 and this just like equivalent sequences or what? Okay. And 2. Okay. So now it can just be like publish section 5.2. Okay. Are we good? Okay. Then next I will want 5.3, which I've also started on. Just make sure. Okay, so 5.2 looks good. Then I'll just collect the cards since I'm also doing these cards kind of as like long-term like quality control because sometimes hard to tell if the cards are good unless you've done them for like a few months and then you start to forget and then you're like, wait, this card is actually not that good. I need to change it. So I've been reviewing my own cards as I make these for other people. Okay, so that's 5.2. Then now we come to 5.3. Then I guess, yeah, it's up here, but not in a very good state. So I guess I'll try to do these cards without looking at my answers. Okay, how can you remember how addition and multiplication are defined on the real numbers? So I guess it's just that the limit symbols can like commute with the operator. Or like it's just like you can think of it as like distributing. Okay, yeah, that's what I said. So why did we need to introduce the idea of a sequence being bounded away from 0? Um, um, so I think it's when we were defining the reciprocal of a real number, and if a sequence is not bounded away from 0, there could be 0 terms in the sequence itself, or it could be converging to 0, so that when you take the reciprocal, it's like this blowing up sequence. Yeah, but this is the tricky thing about these cards. So is this asking about um, those two specific, like what goes wrong, or is it asking you like, oh, this is like when we were doing the reciprocal thing? Or maybe it's something else that I forgot. There are two. Okay, yeah. Um, yeah, okay. So it looks like past me was also like, this prompt is not that good. Um, and was like, okay, I'll just think about this later. And here I am, thinking about this later. So, uh, yeah, we'll need to fix this card. if a sequence AN is such that A, okay, so I guess none of the terms are 0. Um, why might it still not be bounded away from 0? Yeah, so it could be like 1, 0 0.1, 0 0.001, 0 0.0001, and so on. Like all the terms are positive, but then it's like going to 0. So then if you look at uh, the reciprocals, it's blowing up. Okay, so yeah, does the counterexample work? Or is this asking for something else? Okay, yeah, okay, that's good. Okay, so then I guess our task now is first we scroll down to 5.3. I think this is a fairly long section. Yeah, okay. So we have to first fix this second card, and then we're gonna add more cards. So let's see. Um, okay, so like one could be like when defining which arithmetic operation uh, did we need to introduce of a sequence. Okay, so now we're specifically asking um, uh, hmm, interesting that Tao did the bare arrow instead of the maps to arrow. Okay, then we say like um, so I want to make a card for this case. So I'm trying to figure out the best way to phrase it. Um, so if a sequence is not converging, if a Cauchy sequence of rationals is not converging to 0, why might n equals, I used 1 down there. Guess he's using 1 here, so I'll use 1. Okay. It's not converging to 0. Why might the still be undefined? Okay. The sequence might contain 0 elements like 0, 0.9, 0.99. Okay, so we asked for that, and then I think I also want to do the other one. So I say can copy this. If a sequence of rationals does not elements, why might the reciprocal sequence still be or it's more like why might the see in this case what goes wrong is the reciprocal is defined but it's not Cauchy. And then in the other case it's that the sequence itself is undefined because we can't flip this over. So, but do I want to like reveal that in the prompt itself, or do I want to be like kind of maximally vague and verbose by like saying like be undefined or not be Cauchy, or like just vague like why might we still run into problems? See, this is the kind of thing that I still don't know, and it's even harder to know when you're like writing cards for other people. I'll just be like kind of give away the answer in a way. Not still not be Cauchy. Okay. Um, Um, is okay. So I think so now we have broken up this card into asking like uh when what operation we're defining do we do this stuff? And then I ask about both the zero elements one and the converging to zero one. So I feel pretty good about this now. Um, yeah, but still like, so this is, we still haven't, we're like, we've contained all these ideas. Uh, hold on. Oh, we did tie it together with bounded away from zero. Okay, I was worried that we didn't use this bounded away from zero phrase, and then like you might kind of have these ideas, but then like be like unable to tie it back to like what we ended up doing. Um, okay, I think that's good. Um, okay, so I will commit this now. Um, break up zero prompt. Okay, so now let's see if I want to add anything here. Yeah, do I want to add a thing about this? I probably should. I think I'll add it. Okay. Print are two real numbers. Um, I'll just copy from here. Um, and when I guess I'll copy from here. Uh, okay. So, okay, now we've had the equality. Oh, and I think I've been doing this for uh all the other number systems. So I should, for consistency, do this here. So 4.2 is where I did the rationals. So I'll do it here. Yeah, here we go. Okay. it's like kind of a easy card to like uh, make the set not look intimidating. Notation for the set of real numbers are, okay. What set of numbers does R denote? The real numbers. Or I guess I can just say the reals. Okay. Um, uh, okay. Oh, I guess I added that other one too, so I'll just say add more prompts. Okay, so that's good. Hmm. Yeah, like this kind of proposition, it's like everywhere in this book, but like uh very boring to be reviewing in the cards, I think. So I'm not really adding this kind of thing. Um, yeah, addition. So I think, um, yeah, how do you remember? I think how do you remember is better than like how are they defined? Um, like you just want to know that you can like kind of distribute the limit, um, or like factor it out. Uh, and like that's more important than like writing out like all this limit notation. Okay, yeah, this is again like uh pretty like I think it's actually a fairly difficult proof uh at this point in the book, like if you're learning this for the first time. But then like how do you make this into a smaller flashcard? That I suspect the answer is like you shouldn't even try because like if you what I learned when I tried to do this with some proofs that I was interested in is that like it's like you pick out some like piece um and then you like ask about like some parameter or something and you just when you get the card you have to kind of like thrash around in your brain to like remember all the context and then like go through the whole proof in your head almost and just like then get that small piece of information. Um, because I guess, yeah, that's just um, like you don't want to be remembering proofs as just like random facts together. So like you almost you don't want to be able to answer these questions off the top of your head. What you want to be able to do is like see this and then like write this. Um, and that's, I think, better to just practice uh, by like doing exercises or having proof cards where like the card itself is like prove this. So I'm just gonna skip that. Yeah, axiom substitution. This is again, it's like everywhere in this book, and I don't really know how to like put this in. Maybe when I get to the appendix and I'm like converting that to cards, I will do that, but not now. Um, yeah, okay. Okay. Um, then we got to multiplication, and it's just the same thing. Okay. Yeah, I actually want to make a card for this. So, um, if we have a rational number q um, in the formal limit notation, uh, yeah, what real number does q correspond to? Um, I'll flip this around. If we have a rational number q, what real number does q correspond to when written the formal limit notation? Okay. Um, okay. Um, yeah. I was wondering if I should do the like sequence version as well, and like maybe an example. Um, but I think it's fine. Yeah, negation. I'm not sure. I kind of did that for the other ones, but by this point, it's kind of like um, maybe I should. Actually, I don't remember if I did it for the rationals because I remember doing it for the integers. And then when I was doing the rationals, I might have been like, I'll do it when I get to the real numbers. Um, how do we define negation minus x for minus 1 times x? Okay. Okay. Then I guess subtraction, I know I did it for the other ones. ones, but I might still do okay. Yeah, the laws of algebra, I haven't even attempted to convert that into cards by like being like list the laws of algebra or like blanking out like a single law because there's like 11 of them or something. I think it's uh there are better ways to remember that kind of thing. So I haven't tried. Um, and I think it's okay to not know uh the list. Okay, now we get to reciprocation, which is where we started with. Um, yeah. Okay, so I think we got that. Okay, then let's see how long this section is. Oh, not too much more. Okay. Yeah, so then I guess, yeah, how do we define the reciprocal? I guess, yeah, I want a card for like that. Um, okay, here we go. Mm, um, if real number, how do we define the reciprocal? Um, we find some sequence that is both bounded away from 0 and equivalent well, I guess, yeah, I can't say equivalent to because x isn't a sequence. Um, and such that its formal limit is equal to x, and then take the reciprocal sequence. I don't know if that's too long. I think it's fine. Um, yeah, actually, never mind. Yeah, I was gonna be like, do I like it when I see these kinds of formulas, or do I actually like it better when it's like just words? And um, I actually don't know. Sometimes I like one, but then other times I feel like formula is so much nicer. In this case, it's a bit hard to say. Um, so I might just have this in and then keep reviewing it, and then like in 3 months, I might be like, actually this is not the best way to phrase it or something. Okay. Yeah, this trick is a nice trick. And I think it shows up um it showed up once when um forgetting the exact context. It was um I don't remember. It was something like you have a bijection and then like you have a left inverse and right inverse. You want to show the two inverses are the same or something like that. Uh, where this is like it naturally falls out. Um, Here it feels kind of like where did he get this idea from? Because um, yeah, I think like if you were trying to prove this, you would do like you would not do this and just more like try to do something that's like straightforward but also like takes a lot of work or something. Um, yeah, I don't know if I should do it, but I'll do it anyway. Um, how do we define division? Um, okay, okay, so that's probably good enough. So now I'll just fill this in and then say um, defines the numbers as formal limits rationals, then defines the Okay. Multiplication. Multiplication, subtraction, reciprocation, division. Okay. Good. Add more. Okay. So I have 13 cards here. And it's yeah, this page. Oh yeah, I can tell because this got updated. Okay. Okay, so let's do these cards to check. Then if it's good, we can push. Okay, notation for the set of real numbers. Big, bold R. Okay, the reals. When the AN sequence and BN sequence are equivalent. Yeah. Do I want that? I'll just yeah, it's not really necessary. How can you remember how addition and multiplication are defined? We did this earlier. It's that the limit just like distributes. Okay, yeah. If you have a rational number q, what real number does q correspond to when written in the formal limit notation? As the limit, or just q, 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 q. Yeah, okay. How do we define the negation? Minus 1 times x. How do we define subtraction? X plus minus y. When defining which arithmetic operation did we need to introduce the idea of a sequence being bounded away from zero? Reciprocation. If a Cauchy sequence is not converging to zero, why might the reciprocal sequence still be undefined? Good, just checking this notation. It might contain zero elements. Yeah. If a sequence does not contain zero elements, why might the reciprocal sequence still not be Cauchy? It's because it could be converging to zero while being all non-zero. Yeah. Yeah. Okay. If a sequence is such that it's not zero, okay. Yeah, it's the same idea as the previous one. Might still be converting to zero. we find a sequence that's bounded away from 0 and equivalent to x, and then we take the reciprocal sequence. Okay, how do we define the division? X times reciprocal of y. Okay, collected. Why is this one long? Because we're still in debug mode, so I don't see why one of them would already be in my collection, for example. But that's fine, I guess. Okay. And I'll copy that. This section was called okay, delete the debug. Okay. Publish section 5.3. Okay. Then go here. Okay, so now we have 5.3. This is still debug. So now it's there's no debug here, so this is the real thing. I'll just click through to collect the cards since we just reviewed them. So they're all fine. Okay. Good. Wait, the first card was something about the reels. I'm wondering if it's like somewhere in my collection. Huh. Is that possible? Okay. Oh. Aha. Whoops. I made those exact same cards in 5.1. Except I changed the answer. So, here's something I could do. What I've noticed is that Orbit doesn't seem to do any randomization on the interval lengths, so these two cards will always show up together. So I'm thinking I'll keep the first one in 5.1 and the second one in 5.3. That way they'll be showing up separately. And since I already collected the cards on my account, there's nothing to do uh, here, like there's no, in orbit you still can't like remove cards or like edit them or anything, so it's fine. Um, so yeah, that's basically um, kind of what a typical flashcard making session looks like for me for this book. Uh, aside from the talking, I usually just do it silently. Yeah, so that's it. Okay, bye.